Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on December 23, 2025, exactly 2 weeks ago. It demonstrates that large language models can accurately predict their own failures by decoding internal signals, using a new mechanism called Gnosis that adds only 5 million parameters, yet outperforms billion-parameter external judges. The paper is titled, "Can LLMs Predict Their Own Failures? Self-Awareness via Internal Circuits." And as we'll see later, the results on early failure detection are really promising. And for those interested in the implementation, the authors have shared their code on GitHub. And on Hugging Face, the 1.7 and 4 billion parameter models are ready to download, including Python code examples for predicting correctness using internal model signals. Figure 1 illustrates the core concept and its effectiveness. On the left, the diagram shows how Gnosis attaches to a frozen large language model, tapping into its internal hidden states and attention maps as they flow through the network. These signals are compressed by specific encoders to output a single correctness score, effectively flagging hallucinations in real time. The impact is clear in the chart on the right. Across math reasoning, QA, and general knowledge, the orange bars for Gnosis consistently outperform the purple bars for Gemini 2.5 Pro, achieving a 92% OROC in math. So, while Figure 1 gave the highlights, Table 1 provides the comprehensive breakdown across 3 distinct domains. The columns display the different frozen backbone models, ranging from smaller QN3 variants to the larger GPT-OSS20B. Focusing on the first section, math reasoning, the comparison is striking. The bottom row highlights Gnosis, which achieves area under the curve scores as high as 0.96. This consistently beats the massive external judges listed just above it, like the 8 billion parameter Skywork model and Gemini 2.5 Pro, confirming that lightweight internal circuits can rival much larger, separate verification systems. Well, while the previous table showed accuracy, Table 4 highlights a massive efficiency advantage. This comparison tracks latency during long math reasoning tasks. In the top rows, the external Skywork judge slows down dramatically as the response length doubles from 12,000 to 24,000 tokens. However, the Gnosis rows at the bottom tell a different story. Here, the latency stays flat at just 25 milliseconds regardless of length. This creates a 99 times speedup for long sequences, proving that internal verification is not just better, but substantially faster. Alright, to understand how Gnosis maintains that speed, Figure 2 details the dual-stream architecture. On the left, the hidden circuit encoder processes raw hidden states, using adaptive pooling and dilated convolutions to capture temporal dynamics. Parallel to this, on the right, the attention circuit encoder analyzes attention maps. Interestingly, it treats these maps like images, extracting statistics and visual patterns to spot reasoning failures. Both streams then condense this data into fixed descriptors, which keeps the computational cost constant. So, Figure 2 showed the architecture, and now Figure 3 reveals its most powerful application, early failure detection. These charts track performance as the model generates its answer, where the horizontal axis represents the fraction of the completion. On the left, for math reasoning, notice how the red line for Gnosis climbs rapidly compared to the yellow line of the external reward model. Remarkably, Gnosis reaches reliable accuracy after observing only 40% of the generation, which allows the system to terminate failing paths early and save significant computational resources. Okay, while Figure 3 focused on timing, Figure 5 compares the confidence of the predictions. The top row shows the score distributions for Gnosis, where blue indicates correct answers and red indicates errors. In the math reasoning plot on the left, we see a sharp bimodal separation, meaning Gnosis is decisive about what is right or wrong. By comparison, the Skywork model in the bottom row produces much broader, overlapping clusters. This indicates higher uncertainty, which clarifies why the internal approach is often more reliable than the external judge. Wrapping up, 2 big takeaways stand out. First, reliable cues for correctness are already hiding inside the model's own internal activity. We do not need massive external judges to find them. Second, extracting these signals is incredibly efficient, offering a way to stop bad reasoning paths early and save compute. This suggests a future where models are truly self-aware during generation. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.